I see a text, but I don't see any, like a syllabus or
So
what,
somewhere.
everything that we're going to cover in the unit.
It is there.
Syllabus the on
Somewhere.
Canvas, man.
But it also I sent it
somewhere in
the
our group.
group as well.
Me just send it back in our group.
All right. Let me say, I'm not on the phone, so I can not until a little bit from this, I can go sort out. All right. Stability. So let me begin with the definition of what is stable and what is not stable. A system is stable if and only if. 1 second. Yeah. So a system is stable if and only if the limit of the output as t tend to infinity equal m, where m is finite. So a better understanding can be obtained by looking at a graph. So what we are saying is that the system is stable if as time passes, it goes to a finite value. Which we call it m. M can be any number as long as it's finite. So the output is y, and as time passes, the system goes to that value and stays there. And then now, a system is unstable if, not if and only if, the output as time tend to infinity is infinity. So I look at that. So this system up here, so this is stable. So all right. And then we have marginally stable. So a system is marginally stable if the limit y t tends to and this is the modulus of m. So So what do we mean by marginally stable? So this is the So what do we mean by marginally stable? So what it means is that IA, the system oscillates. So marginally stable system is one that follows either the sine or cosine. So it's marginally stable if it oscillates. So what we're saying by absolute value. So if it's positive, usually it goes positive or negative or some form of that. So it stays within those limits. If it's unstable, it's going to go to infinity. And it is stable if it goes to a finite value and stays there. So bearing that in mind, we want to ask some or look at some things mathematically. We want to be able to look at mathematically determine if our system, we put together a system, if it's going to be stable, unstable, or marginally stable. If we want to build an oscillator, then that oscillator has to be marginally stable. If we want to build most of the systems that we want to put together, we require them to be stable, whatever the system is, we require that that system is stable. Now, so let me just go to something else and ask a few questions.
Wait, sir, can you show us a graph for marginally stable for my secondary quick?
Okay.
Sir, the line that
Sir,
goes
can
straight
you-
across. The line that goes straight across, sir. That's just the horizontal axis, or is that the line for
Yeah.
M?
No, that's the horizontal axis.
Oh, okay, okay.
But theoretically, it can be because it still is marginally stable. If
Oh,
it oscillates around a point M as well. So but then this part here is called the DC component. This is still marginally stable. Yeah. Who was asking another question? All right. I can move.
I believe so.
All right. So I want to solve some differential equations from first principle. So let's all right. So we want to solve this from first principle. So we want to ask ourselves some questions.
Sir,
Mm-hmm.
I want to ask a question, but it's kind of related to something that you did last week. So I just wait until the end of the class to ask, right?
Well, ask now because you might have forget and me might have forget. And I will tell you, all right, we talk about that at the end of the class.
It was about the amplifier where we're supposed to work out the transfer function. I saw an amplifier with a resistor, capacitor, and a feedback resistor and an inductor. For how we would we'll work out the transfer function for those. It would be the same as the output over the total.
Yeah, but we're going to be looking at some things like that after we talk about stability. We just want to establish the final thing, and then maybe if you can hand over the screen to you, draw the circuit in question, and then we can look at that and use it.
Okay, sir.
To solve some problem. All right. All right. So this differential equation, we want to solve from first principles. So anybody know what is the approach for this thing?
Sir, the first thing is the D operator, sir. Or M.
All right. All right. So first thing is to write down the auxiliary equation, but I'm going to take it from a little bit more basic. This differential equation says I takes a y value, differentiate it again, add everything together, and I get 0. So basic question, 4 minus what equals 0? Not a trick question.
4, sir.
4. Sine minus what equals 0? Again, not a trick question.
Sine, sir.
2x minus what equals 0?
Sir, 2x, sir.
Why am I asking a full question here? So if I get 0 over here, and I have a function y, and I differentiate it, again, add up everything at 0. From the basic thing of this, all of these things must be the same thing. You can subtract sine and cosine and get 0. There's only one specific value of x that will give you 0. But this is saying no matter what the value of y, what the function y is, I'm going to get 0 for every function of y that I add up. So I must have the same thing. Now, which is the only function that you know of that when you differentiate it, you get the same thing. Every time you differentiate it, you get the same.
E to the x.
E to the x.
E to the x. So therefore, we are going to try y is equal to e to the, I'm going to put a value in front of it just to ensure. So therefore, let me differentiate this. When I differentiate e to the kt, what do I get?
K e to
Sir,
the
1 over.
Yeah.
Now, when to differentiate it again, what do I get?
K square e to the kt.
So now if I take that and take these and plug them back into the equation above, then I'm going to get k squared e to the kt minus 3k e to the kt plus 2 e to the kt is equal to 0. Now e to the kt is never 0, so I can factorize it out. And then I get to get k squared minus 3k plus 2 equals 0. So this is what we call the auxiliary equation. I don't know what else they call it, or the operator, or whatever you call it. So this is the part that is equal to 0. Auxiliary. And it is also called the characteristic equation by us in engineering. The fact that we call so much things by different names would tell you the two branches of people never really got together at any time to straighten out. So we have k squared minus 3k plus 2 equals 0. And we factorize that. That's k minus 1, k minus 2 equals 0. So we find that k equals 1 or 2. So therefore, we write down our solution was e to the kt. So our most general solution, we can put a coefficient before it, don't change anything. E to the k is 1, so it's 1t plus another coefficient, e to the 2t. All right. Now, so these two exponential functions that we have here, if we were to draw e to the t, it would start at 1. And if we were to draw, well, let's call this e to the 2t, just making a sketch. And if e to the t, so e to the 2t plus e to the t, b e to the t, would look something like this. So the question now, based on what we have said, what is it that, is this system stable, unstable, or marginally stable? Based on our discussion before.
Sir, I would say marginally stable. Well, no,
Unstable, sir.
unstable.
Unstable. Yeah.
Unstable.
Yes, sir.
All right. So this is not notes. This is just to establish some things that we want to establish. So now I want to look at d2y dt squared plus 3 dy by dt plus 2y equals 0. So we can jump out of the shenanigans that I did before and just go straight to the auxiliary equation.
Minus 2 and minus 1.
All right, so we have to factorize it. So therefore, y is going to be equal to ae to the minus 2t plus be to the minus t. Now, so that is the solution there. So we're going to make a sketch of that one. The exponential decaying, so it is going to look like that. So this would be, because of the negative, exponential decaying. So this is so my question again now, based on the discussion that we have had before, is this stable, unstable or marginally stable?
Stable, sir.
Stable, sir.
So this one is stable. Like I said, not notes are just establishing an argument. All right, so next one. So this now is k squared plus 4k plus 8 is equal to 0. This one here now, we have to use the quadratic formula. So quadratic formula x equal minus b plus or minus the square root of e squared minus 4ac all over 2a.
So you get minus 2 plus 2i.
All right, minus 2 plus or minus 2i. So now, so therefore, y is going to be equal to a e to the minus 2 plus 2i t plus b e minus 2 minus 2i t. So true, me is a maths teacher from high school. So we're going through some things that might be unnecessary. So we're going to factorize all the e to the minus 2t. And then we are going to be left with a e to the 2i t plus b e to the minus 2i t. Euler's theorem. Anybody remember it? Right, this thing is not working.
No, sir, but you get n cos theta n cos t plus m sin t.
All right, so right. Having a problem, we can't get the mouse has decided to take a walk. It happens. Give me a second here. Okay. All right, so Euler's theorem says e to the I theta is equal to sine cos theta plus I sine theta. So e to the 2i t is going to be cos 2t plus I sine 2t, and e to the minus 2i t is going to be equal to cos a minus 2t plus I sine minus 2t. But they tell you in trig class, cos and minus theta and cos of theta are the same thing, so you're going to get cos 2t And I tell you, the sine of minus t is
minus.
Let's put the minus outside. So now we are going to add these two together. This is A. Like I said, this is all rough work. But like I established things from first principle. So this is A plus B, if I add them together, cos 2t plus AI minus BI sine 2t. So when you add two constants together, you get another constant. So therefore, we're going to write this as m. A plus B is m, because we say so. And AI plus minus BI is n sine 2t. So so what we are going to end up with is y is equal to e to the minus 2t m cos 2t plus n sine 2t. So if we make a sketch of that now, this is oscillatory and this is exponential decay. So what we are going to end up with is let me try to write a little bit better. Something like this. So this is the e, the minus 2t part, the exponential decaying part, and this part is the m cos 2t plus n sine 2t. We don't care if it don't look so wonderful. Like I said, I just want to establish something. Question: is this stable or unstable?
Sir, it's stable, sir.
It's stable because it is going to, it's decaying to zero. So it is stable. All right, the final thing to establish my argument is this now. Like I said, this is not notes, this is just using something that you so that we can.
Sir.
Yes.
Before you continue, sir, you can just run through that formula one more time, sir.
Which part?
Just from the top, sir. Right here, sir. Right here, the theorem, yeah.
All right. So what we have is e to the 2it plus b e to the minus 2it. So we're using Euler's theorem, and then we're going to replace the theta by 2t in the first case. So everywhere we say theta, we're going to put 2t. And then we're going to replace it by minus 2t in the second case, in the case up here. So it's minus 2t that we're going to replace it by. So the second one we say cos minus 2t plus I sine minus 2t. Now, cos of minus theta is the same thing as cos theta. That's they prove that in trigonometry. And sine of minus theta is minus sine of theta. They also prove that in trig class. Some of we did not pay attention, some of we never did not pay attention. But we tell them, you say, it is so. So, therefore, now, we can write the cos of minus 2t, we just write it back as cos 2t. Sine of minus 2t, we write it back as minus sine 2t. I put the a, because we have the coefficient a in front of the e to the it A cos 2t plus A sine 2t, and I put the B in front of, it don't look like a B here, but it's a B. So now, what I did was add these two together. So that's A plus B cos 2t. And then I add these together, AI and minus BI, to end up with AI minus BI sine 2t. A plus B, I must call it another constant. I can call it C or A, X or Y, or well, we're not going to call it X or Y. So we call it what the math people call it M. And this 2 is another constant, so we're calling it N. So our solution that we had here for here was, when we put the two of them together, we can say M cos 2t plus N sine 2t. So the thing about it now is when our roots of the equation k equal was minus 2 plus or minus 2i, the minus 2 goes to the exponential part, and the 2 goes to the trig part. So we in maths class, they just tell us to write on the solution. You can just write on the solution straight off the bat. E to the minus 2t, m cos 2t plus n sine 2t. So that is the solution from that equation up there when you have these roots. So we're saying that if you sketch a graph, this part here is oscillator, and this part here is exponential. So it is going to kind of look like this, but this is the graph that looks so wonderful. But it's an exponential decaying graph. So the question that I ask, which is the most important thing, is whether it is stable or not. And because it is going to 0, which is a finite value, then it is stable. So that is that here.
Yes, sir. Thank you.
All right. So now, last one. And again, write it down this study to right now because there's no test that I'm going to ask you this now. I'm just establishing what I'm going to ask you the test in any test that you get. All right, so now solve this one. So this one here now is k, well, let me write down the auxiliary equation. It's k squared plus 4 equals 0. So k would be equal to the square root of minus 4, which is plus or minus 2i. So therefore, y is going to be equal to, remember, I can write this as 0 plus or minus 2i. So remember what we said, this is the exponential part. So y is equal to e to the 0t m cos 2t plus n sine 2t. Anything raised to the power 0 is 1, so y is equal to m cos 2t plus n sine 2t. And at some point, maybe, if you remember, if you had a cos x plus b sine x, it is going to be equal to a squared plus b squared sine x plus alpha. You remember seeing anything like this anywhere in your life? You can say no, you know.
Sir, repeat that again, sir.
No, I was saying that if you ever see the formula that I have up here.
No, sir. First I see.
Mm. All right, so it exists. You can combine two Triggs equation into one, where the A plus B squared, the square root Pythagoras theorem, is going to give us the amplitude and the sine x plus alpha. Well, for us in electrical engineering, the alpha that is going to be the phase shift. The phase shift just tell us where the curve start from. So a sine wave, it start from here. Alpha tell us where it start from. What angle? So if this is 60 degrees, or whatever value it is in radians, it starts at 60 degrees. It don't start at 0. If there's no alpha, then the curve starts at 0. But if this alpha, it tells us where it starts from. And they call that the phase shift in the graph. So combine this and we put it together. We can ask is who did say they've never seen it before. I just need to. You can ask your personal question.
Yes, sir, but it's not gonna be personal anymore.
No, you didn't go 6-1?
Yes, sir.
You do pure maths?
Yes, sir.
I like you tell them. I tell them. Maths teacher did do it. All right, the teacher did put R yourself.
Sir, yeah, talk, but sir, we do that long time, man.
You see that? Also, somebody if you ask him, how is school, so we can go tell the maths teacher because we know most of them know. If you come through UTech, they do it as well. But they might not do it if you didn't come college. When they come college, maybe. You know?
So, we know that equation, man. With the R, me recognize it now.
Okay, so R is A squared plus B squared. All right, so all I'm saying here now is so this m cos 2t plus n sin 2t, we can write it down as y equal r cos, r sine, don't matter, 2t plus alpha. So basically, this is our y and this is our t and this is the graph. So the question that I'm asking now, is this marginally stable or not? Is it stable, unstable, or marginally stable?
Marginally, sir, because it don't tend towards 0 or any other thing.
Right, so it is marginally stable. All right, so we have enough evidence for a conviction now. We say that if it's going up, it's unstable. If it's going down, it's stable. So if it's going down, it's stable. If it's going up, probably up there. If it's going up, it's unstable. And if it oscillates, it is marginally stable. All right, so back to what we were saying now. One of the things that you will notice is that if it is stable, then the roots are negative. If it is unstable, the roots are positive. So unstable roots are positive. Stable roots are negative. But let's look at this one here now. This one here is oscillatory and stable. But if you look at the roots for this equation, it is the real part of the root. If you look at this, it's still negative. So the real part is negative. And then if it is marginally stable, the real part of the root is 0. So here's a statement that we are going to make now under all of this that we have been talking about. So go back over here so to the notes.
Wait, what was that part they just noted a while ago for the marginally stable root, sir? That the
It's 0.
Oh, the real part is 0.
So now, so we are going to write down now that our conclusion a system is stable if and only if the real part of the roots of the characteristic equation is negative. All right, so a system is stable.
R0.
No, a system, so let me put a system is marginally stable. If the real part of the root is 0. And a system is unstable if any one bad apple spoil the whole bunch of the roots have a positive if you have a positive real part, it's unstable. Real part is 0, marginally stable. And stable if the real part of the root is negative. So that is what we want to establish. All right? So that is what we want to establish this afternoon in our discussion. I should put an S on here. So now, so we want to use that to assist us here. So we can look at a problem. Oh, before we look at a problem, I just want to establish one final thing. Two. Should have done it last week, but it's never too late. Right, tell me we can move on now.
Look like ready, sir. Well, I assume we are.
All right, cool. So we move it on their protestations then. Here, no protestation. All right. Yeah, I should have talked about this last week, but I did. All right. So when we have feedback, all right, so the output is Y. So therefore, it's going to be fed back. Y is going to be fed back here. And then the output of a system. So over here, we're going to have H, Y. We are saying that we have negative feedback. So you have X and you have Y being fed back. You're adding the X and you're subtracting the HY. So here, you would have X minus HY. You follow me up to there?
Yes, sir.
Yes, sir.
All right. So now,
Wait, sir, before you continue, sir, what is the TS stand for again, sir?
transfer function.
Oh, okay, okay.
So now, so the rule is that the output is Y and the input is X minus HY. So Y is supposed to be equal to G multiplied by the input, which is X minus HY. So Y is equal to GX minus GHY. So we are going to make Y the subject of the formula. So we're going to carry this over there. So we're going to end up with Y plus GHY equal GX. Factorize out the Y. 1 plus GH equal GX. So we can write therefore that y over x, which is the output, over the input, which is the transfer function, is going to be equal to g over 1 plus gh, which is a useful formula for your control class. Alright.
Sir, one question there.
Mm-hmm.
Earlier in the diagram above, you said G that the supply or the forward term that is, sir?
That G,
Yes, sir.
yeah, is the, what are you calling it?
Forward or lead, something like that, sir.
No, you hear that in another class. They call, you have the plant, and then you have the compensator. And some of the is called the lead compensator or the lag compensator. Now, when you put them together, that form the G. All right. So this thing here so is a controller or compensator. Now, remember when we were talking about the phase shift? So the compensator supposed to either move this, so this alpha here is a phase shift. So it's either going to move it this way or that way, depending. The compensator is supposed to move it in one direction or the other, depending on the what you want. Now, bear in mind that what we said is that if you add, if you take a controller and add it to the plant, then we're going to multiply the two together. I keep on forgetting, so you're not seeing the pen. So controller and plant is going to change the transfer function of the system. If you add a controller, let's just say this is 1 over s plus a, and this is 1 over s plus b, for example, and I put them together, then the roots of the characteristic equation going to be minus a and minus b, and not only minus b alone. And if you recall, then that is going to cause this thing, this alpha value, so to shift. So the compensator is just there to shift this curve that we have here forward or back. So that is what they did here. Some class somewhere about lead compensator or lag compensator. But is when you put them together, these two together, multiply them to get the G, then so let me see if I answer your question properly now. Yes, it is a compensator, but no, it's not the compensator because it's a compensator plus the plant. Compensator times the plant, multiply them. I don't know if that answers your question.
Proceed one, sir. Respect.
All right. We're about this because.
Sir, which topic is it about?
Huh?
About the compensator and the plant. What topic is that?
Control systems.
Or is that a module, sir?
No. That is a course where you have to do. So I don't know if it just start with yet or in due course you will do it, but you have to do it.
I cannot teach it, sir.
Me? Why? We stick to the evils that we know. And this is one of the evils that we know. So control is one of the evils that I know. So we stick to the control. Thank you. Sorry, signals is one of the things that we know. So we stick to signals. That is something. I need to remove this and this thing.
Sir, so like this equation that you give the output over the input, is that like universal to this application, or will you have to read on control system?
You mean if this formula that we tell you, this down here?
Yes, sir. Y over X
is universal. It applies to every system, every control system, but almost every system is a control system. Whether it be political, religious, some of them are called open loop, where the output, you put in the input and you look at the output, you don't look and see what it is that you're getting out. All right. If you have a school system, it's still a system. You put in the teachers, the teaching, and you get the results. And then you're supposed to eyeball the results. And so we look at the results, and then we're going to make some adjustment to the teaching to get a different set of results if we want to change it. If it's economic, you put in a certain amount of money, you get out a certain amount of, let us say, US dollars, you look and see how much you get, and you make adjustment so you can make more. If you look at everything in life is a control system, because most of the things that we human beings have, we want to control. Whether it be another human being, or the amount of money we have, or the voltage and the output of our, we want to control it. You know, so? If it's a girlfriend or a boyfriend, we want to control it and produce.
Proceed, sir. Yeah, man, sir. Proceed.
So this is a universal rule. You put in the input, look at for your output, you adjust it so that you get a different output. Nearer to what you want. That is what you're supposed to do.
1G would be the system and H is the feedback.
Yeah. So let us not go universal. For example, let us say that this is you have a motor controlling a satellite dish. And you want to control the angle theta. So the motor is turning the satellite dish. When it reaches theta, when you reach the angle, let's say 60 degrees. H is not going to be 60 degrees. 60 degrees is the position, 60 degrees is going to come back and you're going to convert it to a current. So H, what we say H is going to convert a position to a current or a voltage. You know, so? And we're going to look and say that current or voltage corresponds to 60 degrees. So let us say that the feedback says 59 degrees or 58 degrees, the position is. We are going to be feeding 60 degrees. Via some other conditioning, we can put 60 degrees. When you turn the dial and put 60 degrees, you are going to multiply, do something, and it's going to convert it to a current or a voltage as well. And then, so the current, so they said this current here is, for argument's sake, for 60 degrees corresponds to 5 volts. and this 58 degrees corresponds to 4.8 volts. Then the 0.2 volts is going to be fed to a controller that going to take the 0.2 volts and multiply it so you can get the 10 volts that you need to continue turning towards the 60 degrees that you want. So this is my G. So let's say that this is amplifier. The controller is amplifier. We amplify the 0.2 volts to 10 volts. Now, some of the things that we are concerned with is that when we amplify, is this thing going to cause the output to oscillate, go to the 60 degrees and stay there? Is it going to fly past the 60 degrees because it's too much voltage on the motor? So we create an unstable system and it's going to go and boom and lick up and mash up it. So all of those things are things that we are concerned with. All right? But this now will be my G. And this will be my H. So H is just, all of these things are just modifications of like position to convert it to current or voltage. You have your feedback and your feedback from your system is going to convert it to a value that is going to run your motor, that is going to cause this thing to turn to the value that you want to turn it to. And sometimes you want to turn it slowly, or sometimes you want to turn it quickly, and all of those things. So all of those things are what issues that we are concerned with in any system at all. You know, so I look at everything as a system. So let me go to my pet peeve, which in Jamaica, because we were colonized. You have conquered people and colonized people. The conquered people are like Chinese and the Indian. We were the colonized people, like Africa, except South Africa. I think they were conquered. Yeah, they were conquered. So here's what our problem is, and that what I would like you to not be when you turn engineer. You have the system, you have the output, you have the input. It's your output. Sorry, should put output here, so put system here, so this is output. You have a system. In every situation that I have seen, colonized people say the system that we get is perfect. We don't want to change nothing. Whether it is school system or the church system or the electrical system or the mechanical system, what they give it is perfect. So if it's not working, is the input we blame. So we have a school system, and there's everybody but oh, it now produce what we don't want to. If we did only have better teacher, if we did only have better students, nothing wrong with the system. Nobody examines the system. Boy, we're not getting enough light from JPS, boy. And the training, you know, some of them go to UTech and they don't get no proper training, and some of them go to U and them even worse and do this, that. It's always the input. Nothing wrong with the system. Because it was handed to us from on high. Please learn from this course that everything is a system, and sometimes you need to examine the system. Not only the inputs, because every single time with not touching the system, but blame the input. It's either the input never get the proper training, or the input never this, or the input never that, but we're not trouble the system. And most of the time it's because we don't understand the system.
So, sir, I say, in other words, you feel like integrate or pull up the system then and see what really are going on.
You must look at the system, see what is going on, do some research. Other people have other systems. is that the system that would work best for you before you start blame the input now. Before you start blame the input now. You know, car not drive fast. Oh, the tire, them know, boy, you have better tire. And it's always if you did a better this, if you did a better that, if you did a better that, if you did a better that. And that is a characteristic of colonized people. That's not a characteristic of colonizers.
Oh, sir, sorry to interrupt, but to my knowledge, it seemed like you could use a pump to explain it, because you know, configuration uses feedback. So
yeah, the APAM is a feedback system. Same, almost every system we have is a feedback system. Although some of them is open loop, we don't look at the output I use the output to help modify what the input is. And like I said, there's a controller, and that controller modifies the system. Anyhow, I digress, kind of. Yeah, let me, while I'm rubbing off this, let me use another example. When a person from the Netherlands comes to Jamaica, they always, you saw some people who used to come from the Netherlands here that I had interaction with. They always ask, so why when you buy these big engine cars? And the response, no, because we like them. So, oh, so no do have them there in the Netherlands. No, we don't buy them there in the Netherlands because Netherlands flat. You know, no hill to go up. So their thing is that the usefulness of what the system that they are going to employ must be such that it is economical and feasible for what it is that they are going to do. They're not into the bling array. We, like I said, colonized people into the bling and the array. So we always get systems that do have nothing to do with what it is that we want to do. Things to carry us from A to B, we get a system, i.e. a car in this particular case that I'm talking about, that is not economical, burn too much gas, and all those type of things. And then we now start blame, why insurance company at the bad road, them had this and that, all of the input them. We just tend to be like that. And like I said, it's colonized people who tend to be like that. Because the colonizers have told us that anything them give it, that is perfect. And so left it alone. Anyway, back to where I was. So let me so let us examine the question here now.
Never grounded the circuit too, or was it not intentional?
Sir, are you there?
Yep. All right. So we want to look at this problem here. So first thing, we have to find the transfer function. So not how to find the transfer function, but what is the first thing that we are going to do based on what we said last week?
So do apply Laplace transform to get the circuit or divide the circuit. That is one.
All right, so we divide the circuit.
And find the Laplace of both the input and output of the component, or the Laplace of the components.
All right, so we're going to call over here G2, over here G1. So let's do G2 first. All right, so this is going to be the output over the input. So it's 1 over the total, which is 1 over S plus 1. Is 1 over, from our denominator is S, 1 plus S is going to be equal to S over S plus 1. They flip the dividing fraction. So that's G2. So up here, You still hearing me?
Yes, sir. Yes, sir.
Yes, sir.
All good. All good.
All right. So this would be my Z2, and this will be my Z1. And we know that this is minus Z2 over Z1. So Z2 is going to be 1 over S plus 1 over 1. And we'll put the minus down here. So that is going to be equal to S 1 plus S divided by negative 1. So that is equal to S plus 1 over S minus. Seriously, I never planned on this. I have to change the problem here. I just took one out of my head and then I realized that there are major problems. So I'm going to, sorry about that, I'm adding something to it. So I'm adding a capacitor up here. All right, so this would be, so we can work out by this now. I put it in a capacitor. So let me work out back this. So minus Z2 over Z1. So it's going to be 1 over S plus 1 over 1 over S plus 1. Yeah. I don't know. We ain't gone for a walk apparently. So let me make this 2. I wanted the reason why I just want one that will, where we can talk about stability in a proper way. So this is 2. So this is 1 over 2S. So this is 1 over 2S. So this is going to be equal to, when I put everything together, this is 1 plus S over S. And then this is 2S, 1 plus 2S. So it's 1 plus S over S multiplied by the denominator is going to be 2S. This part here, when we flip it, is going to be 1 plus 2S. So that cancels that. S plus 1.
So should did they take out the negative sign?
So put the minus sign at the end of it down. All right, so the TF is G1 times G2, which is equal to G1 is minus S plus 1 over minus, this thing here giving me a lot of problems. All right, minus s plus 1 over 2s plus 1 times s into s plus 1. So therefore it's going to be s so it's going to be minus s over 2s plus 1. That's my transfer function for my system. So here's the thing now. The characteristic equation and the auxiliary equation are the same thing. The characteristic equation set the denominator of the transfer function to 0. So my characteristic equation or my auxiliary equation is 2s plus 1 equal 0. And so the roots would be s equal negative a half. So is that stable or unstable?
So it's stable because the root is negative.
Right, so the system is stable because the root is negative. Plus, all right, so what we're saying is that this represents the differential equation of the system. All right, I'm going to ask you to work out this one. Take a few minutes.
Answer.
Me hearing you.
30. It looked like you should have a negative VI since
Yeah,
the negative sign was on the bracket.
yeah, that's correct. This thing is giving me pure problems. So now it comes up. All right. So there are many ways to do this, but I'm advocating that you
Sir, you can divide the circuit in three, sir.
no.
Not gonna work, sir.
You have a problem because you need you don't need another resistor or something, right? Just
Oh yes, sir.
for it to work properly.
Yes, sir.
I was going to say yes, but all right. So try and tell me where you get, and then come back after a few minutes and discuss it. Tell me when you get it.
So as in you just want us to get the transfer function part first?
Yeah.
Okay. Sir, I got something, but I'm not sure if it's correct or not.
Yeah, tell me what you got. And I'll tell you. If it's the same thing that I got.
S over 2s cubed plus 3s squared plus 3s plus 1.
Correct.
Sir, I get S over 2s plus 1 all squared.
No, I disagree with that one.
Okay.
All right, so what you got for G1? This part here, so which is 1 over 2s.
S1 over 2s plus 1 for G1.
Yep. So that would be 1 over 2s over 1 plus 1 over 2s. And when you simplify that is 1 over 2s plus 1. All right, so G2 now. This is s, and this is 1 over s. So parallel part would be product over sum that works out to 1 over s squared plus 1. So that is s over. So the parallel section is equal to s over s squared plus 1. That's the parallel section alone. So now the G2 would be equal to the parallel section over s over s squared plus 1 plus 1. And when you simplify that, you get s over s squared plus s plus 1. So the transfer function that you get is going to be multiplied this one and this one. So it's going to be 1 over 2s plus 1 times s over s squared plus s plus 1. So that's going to give you s over. And I'm going to leave it like this. Now, so that is the transfer function. The Next question I must ask that is the system stable? So we're going to say 2s plus 1 times s squared plus s plus 1 is equal to 0. So we use a quadratic formula or MATLAB. So 2s plus 1 equals 0 implies that s is equal to negative a half, and s squared plus s plus 1 equals 0. Whatever method we use. What I got was negative a half plus or minus root 3 over 2i. So based on what I get, is the system stable or not?
Sir,
Stable.
it is stable, sir.
Right, so the system is stable because both roots are negative. All right, so here's, I just want to mention a little bit what we have here. So can I go on to just mention something in closing? All right, so I just want to mention that in one of the books that I sent, we are going to be dealing with chapter 1, 2, 3, 4, 5, 6, 7, 8, and 9. So next week we're going to be looking at chapter 9. What I would like you to do is look over chapter 1 and chapter 4 in particular. For example, chapter 1, chapter 1, these are some things that I don't deal with. So, oh, this is chapter 2, sorry. Chapter. Yeah, so some of the things that I would like us to look at, and some of the questions at the end of I need to look at the end of chapter 1 at the questions that are there and see if you can do them, or whatever you can do. Next week you bring them come. I'd especially like you to look at this example 1.9. So look at the example and the solutions that are there for chapter 1 and chapter 4. I'd like you to also look at chapter 4. It has to do with Laplace transform applied to circuit analysis. All right. So those two especially. Next week we're going to be talking about chapter 9. All right. If you follow the outline, you see that is one, then discrete signals, and then we're going to do chapter 5, which is state variables and convolution. Well, we're taking a shortcut through convolution. 7 and 8. All right, so we're going to stop there for today. But I would like you to take a look at chapter 1 and chapter 4 to see if I'm telling any lies. You don't have to really look at chapter 2 and chapter 3. Just skim through them to see if to make sure you have a cursory understanding of what is going on. All right. No, we know. So when we tell them, say, go look in, look. Tell any student, they go look in our book. It's like you're telling them a bad word. But I would like you to look in the book and chapter 1 and chapter 4. For me. And the next week we will talk about chapter 9. Okay?
Okay.
Yeah,
Sir.
that's all right.
Okay.
All right. So we're stopping here for today.
So you said chapter, question 1.9.
1.9.
No. Yeah, example.
Example
1.9. All right. 1.9. All right. So we're stopping here for today. So next week. Okay?
All right, sir. Next week, sir.
All right.
Okay.
Excuse me, sir, before you go. Can I find the recordings? Recordings.
Something going wrong with the sound, you know.
Chairman, after you can find the recording.
The last 2 set of recordings for the last 2 classes in the group.
All right, so I joined the group late, I believe, the signal group. So
I did it in the group description.
So it's to YouTube. It's on YouTube.
okay.
All All right, when I get the phone, I will send it back. Put back the link in the group.
Alright, just check the group description and you see recordings.
Okay, check the group description. Thank you, sir.
Sir,
Mm-hmm.
Could you go back to the board? The first example that you did when you were finding G2. Not sure if I wrote on the wrong thing or something.
This one here?
Oh, yes, sir. When you have G2 equals 1 over 1 plus S over S.
G2 would be 1 over S plus 1. So it would be, that would be my G2.
Sir, is that the product over the sum or a parallel?
No, for this G2, it is the
Voltage divider rule.
Voltage divider rule. So it's the 1 over the sum of the 2 that are here, over S plus 1. So we use a voltage divider rule for that.
Sir,
Mm-hmm.
for G1, right, sir, you have the answer as S plus 1 all over 2S plus 1. You know, it be 2S plus 1 all over 2S plus 1, which is negative 1. Because up top you have 1 plus S over S times 2S over 1 plus 2S. And S them cancel.
Mm-hmm. So what I did with this was write it as 1 plus S over S divided by 1 plus 2S over 2S. And then you get 1 plus S over S times 2S, 1 plus 2S. Oh, I left out the 2.
Yes.
Yeah, so this will be 2S plus 2 over 2S plus 1. Yeah, we'll leave out the 2, so remind me next week, so we correct that. So times 2. Yeah, this thing give me a lot of problems to manipulate today. I don't know what is the issue. Because of unstable internet connection. So granted, so it don't really it affects the transfer function. So the transfer function should have a minus 2. Yeah. Where should the 2 be now? It should be times 2.
So TF will equal.
Sir, the TF
minus 2.
Sir, it would be minus 2S over 1 plus 2S.
Right. So I left out the 2 is
The
missing.
differential equation now, it's supposed to be minus 2D VI or V naught 2D V naught.
Mm-hmm. So this is 2D V naught over dt. Wow. All of a sudden the thing turned purple. Not even as well. 2D V naught dt plus V naught equal
the So either way, it'll be minus
minus
2 dvi by dt.
Yeah, this should have a 2 and this should be so the 2 mistake that makes this may use instead of this. So this there's a problem. So this should be the transfer function. And so this should be the differential equation. It don't affect this because it's the same characteristic equation. All right. Remind me to talk about it next week. All right. All right. So anything else?
Sir, when you're finding G2, use the voltage divider rule. Because did you find the Laplace of the voltage or something?
No, what I did was find the Laplace for the write down the Laplace for the each of the elements. So you write down the Laplace for each of the elements. And for the section without the op-amp, you use the voltage divider rule. For the section with the elements, you use the op-amp rule that says Z2 over minus Z2 over Z1. Take out up here Z1, Z2, sorry. Take out over here Z1. And you proceed. Use Z minus Z2 over Z1. But this one here now, over here is Z2 over Z1 plus Z2. Voltage divider rule that is used. But you write down the Laplace transform for each circuit element before you apply either the gain for the op-amp or the voltage divider rule. All right.
Yes. So you can always just drop the voltage, or you don't consider it.
You can always, you don't have to consider the voltage when you're working out the transfer function, because it is the ratio of the input to the output voltage that the impedance is. When you find the impedances in terms of the Laplace, that so you don't consider the voltages unless you're asked to find the differential equation also for the system. All right.
Yeah, thanks.
All right. So next week